On the night of 11th February 2022, the Zwicky Transient Facility, located at Palomar Observatory in California, detected a strange flash of light in the sky. It sent out an alert about this unusual source of visible light. As many as 21 telescopes observed this unusual flash in various wavelengths, including the Hubble Space Telescope and the NICER X-ray instrument aboard the International Space Station. After studying it for 2 more nights, the event was flagged as atypical because of its rapid rise and fall in luminosity. Astronomers reported the source to the Transient Name Server, which assigned it a formal name, AT2022-CMC. When they observed this source across the entire electromagnetic spectrum and analyzed the data, they realized they had witnessed an extremely rare cosmic event. The bright flash of light was emitted by a black hole eating a star halfway across the universe. The jet of stellar leftovers was blasted directly toward Earth, making it visible in the sky as a bright flash of light. But how did astronomers find out that it was a black hole eating a star? What happened moments after the black hole disrupted the star? Finally, and most importantly, why was this discovery so important in astronomy? The universe is not as calm as it seems when we look at the night sky. It can be a violent place. Stars die or collide with each other, and black holes devour everything that gets too close. These and other events produce flashes of light in the night sky that astronomers call transients. A tidal disruption event, or a TDE, is one such event in which bursts of electromagnetic energy are released when supermassive black holes at the centers of galaxies disrupt a star that passes too close. The star is violently ripped apart by the black hole's gravitational tidal force. That's similar to how the moon pulls tides on Earth, but with greater strength. Then, pieces of the star are captured into a swiftly spinning disk orbiting the black hole. Finally, the black hole consumes what remains of the doomed star in the disk. Such dynamic events provide a new window to study how supermassive black holes disrupt any object that gets too close to them. So astronomers actively look for such events in the sky surveys, and the Zwicky Transient Facility is currently one of the most extensive transient surveys. When AT2022-CMC was discovered, astronomers first studied the source across the entire electromagnetic spectrum. In the X-ray, radio, and submillimeter wavelengths, this source turned out to be among the most luminous ones ever discovered. This is the light curve of the event in optical and ultraviolet wavelengths. The x-axis represents the time from the first detection in days, and the y-axis is the apparent magnitude. In astronomy, the lesser the magnitude, the brighter the object. Astronomers noted a red color and a dramatic rise and decay for about 4 days post-discovery. The evolution then slowed, and the color became bluer. This is the Hubble Space Telescope image of the event. The exceptional luminosity across the entire electromagnetic spectrum and its rapid evolution on a timescale of mere days made AT2022-CMC extremely unusual. Astronomers have been discovering about 100 energetic transients every night, but none of them have such unique properties. So they wanted to know what caused this bright flash of light, and the answer was in the light curve. In their paper, the team compared AT2022-CMC to 3 known transient classes, which exhibit fast optical variability and the existence of radio and X-ray counterparts, kilonovas, gamma-ray bursts, and luminous fast blue optical transients, or LF-BOTs. Kilonovas are transient astronomical events that result when 2 neutron stars or a neutron star and a black hole merge. These events produce many chemical elements heavier than iron. The first neutron star merger was detected in 2017, and the initial color and rapid growth of the light curve of the two events resembled each other. But there were two main differences. First, the luminosity of kilonovas is expected to be orders of magnitude fainter than AT 2022 CMC due to the low ejecta masses expected. In addition, kilonova models evolve from blue to red as the synthesized elements are produced, whereas this transient evolved from red to blue. Astronomers then compared this event with a prototypical luminous fast blue optical transient, or an LF-bot. It's a poorly understood class, likely related to the stellar collapse to form a black hole. The X-ray and radio counterparts of the two events resembled each other, but again, astronomers found two key differences. AT 2022 CMC was much redder than a typical LF-bot. In addition, no LF-bot has been discovered to date with a long-duration blue component. These properties strongly disfavored this scenario. Finally, astronomers compared this cosmic event with a typical gamma-ray burst, or GRB. The high luminosity, red color, and rapid decline are consistent with the afterglow of a gamma-ray burst. But the only difference is that the radio and sub-millimeter emissions were long-lived, and X-ray emission was variable. The signal remained 100 times more powerful than the afterglow from any gamma-ray burst seen to date. These points indicate that AT 2022 CMC is not even a gamma-ray burst, so the only possibility that matches all the observed properties is a tidal disruption event that formed a relativistic jet. The event started when an ill-fated star approached the supermassive black hole on a nearly parabolic trajectory and was ripped into a stream of gaseous debris. About half of the mass stayed around the black hole and produced strong shocks at the self-crossing point. The shocked gas then circulated to form an accretion disk around the black hole, whose rapid spin generated a pair of relativistic jets. The event occurred at a redshift of 1.19, or about 8 billion light-years away. This makes AT 2022 CMC the furthest jetted tidal disruption event discovered to date. It's so bright that astronomers calculated the black hole is eating about half the Sun's worth of mass each year. If the James Webb Space Telescope discovers the host galaxy, then the transient position should coincide with its nucleus, because the event was caused by the tidal disruption of a star by the supermassive black hole at the center of the galaxy. There are three important things that make this event extremely special. The first is that it had relativistic jets, in which particles are accelerated to 99.99% the speed of light. Only 1% of tidal disruption events produce jets. The second is that the jet was pointed right in our direction. And lastly, this was the first TDE that could be observed in optical wavelengths within hours of its occurrence. The last time we saw such an event was more than a decade ago, but it could not be observed in the optical wavelengths. So this is the first time a black hole in such an action could be seen in optical wavelengths in the night sky. The cosmic event could open up a new way of detecting these jet-firing TDEs across the vastness of space, thus allowing for the deeper study of these rare events and the black holes that trigger them. This concludes the 37th episode of the Sunday Discovery series. So if you've enjoyed this video, make sure to like it, subscribe to our channel, and press the bell icon so that you don't miss any future videos of the series.